Now that we have assembled all the ingredients for describing a memory model, the next is to describe the entire space of memory models, memory consistency models. So where do we stand right now? So what we have been observing is that sequential consistency is not practical. Processors reorder instructions that access different addresses, not the same, but that access different addresses for performance reasons. So for a uniprocessor, it doesn't matter, but for a multiprocessor, it definitely does matter. And we have seen very non-intuitive behaviors because of this. So for example, uh, some pieces of code, some reorderings which are perfectly normal and perfectly correct in a single threaded execution would appear to be incorrect in a multi-threaded execution. Furthermore, given the complexities of the pipelines, non-blocking caches, and so on, writes can be non-atomic. In fact, they are non-atomic in a lot of architectures, such as IBM and ARM. So we need to have a model that also takes this into account. So now the question is that given a non-sequentially consistent system, which is any practical system, how do we reason about its correctness? So SC pretty much gave us a mechanism where we could map a parallel execution to a legal sequential execution, establish its equivalence, and then we could say that look, given a piece of code, these are all of its legal sequential executions. So what we could do is that given a piece of code, assuming the architecture follows SC, we could create a space of legal sequential executions, LSE1, LSE2, so on and so forth. If all of them follow a certain property, for example, if all of them after the execution set the value of some variable to equal to 3, so we can say that regardless of how we execute, because a parallel program can have many different outcomes, but that's okay as long as all the outcomes y is equal to 3, we might be happy with it. So what can we do? Well, we can reason that look, regardless of whatever happens, as long as our machine is sequentially consistent, we can enumerate all the legal sequential executions, and we can say that look, in all of them the common property is that y is equal to 3, which is what I want, hence I'm happy. But what about non-SC executions? Things become way more complicated in this case. So in this case, what exactly we see is that even enumerating all the executions, and particularly the sequential executions, is hard, and many sequential executions also might not be legal. So let's understand this. So let us study this. All right. So what we want to do is that we want to create a theoretical tool which is somewhat similar to what we did in the case of sequential consistency, which basically was to convert a parallel execution or somehow equate it, establish an equivalence with a sequential execution. In the case of sequential consistency, this was very easy to do, and the sequential execution was very elegant. So why was it very elegant? Well, number one, it was legal. Number two, program order was preserved. So we will not be that fortunate when we consider non-SC models. So what we will do is, from a parallel execution, we'll create a graph, a specialized graph called an execution witness. And from that, we will move to a sequential execution, which may or may not be legal. So we will see when it is legal and when it is not. But this will at least give us several things. One is that if we can construct a sequential execution from a parallel execution via an execution witness, what it can at least tell us that for a given memory model, it's a valid outcome, right? So the mere fact that we could traverse this will tell us that look, given this execution, so let's say my question is that given an execution, is it valid? in the sense, are the outcomes valid? So what I can do is I can create an execution witness out of it and then try to create a sequential execution out of the execution witness. If I'm able to do it, at least I can say the outcomes are valid, right? So I can use this method to enumerate all the valid outcomes, and as long as they follow a certain property, I am happy. So this is slightly more complicated than the simple two-step process that we had in the case of SC. So in this case, it's a three-step process, but we will see that this is very elegant, and of course the two-step SC process is a subset of this. So let's take a look at some of the broad principles. The first is that given a piece of parallel code, it can have many different executions and it can have many different outcomes, right? So the set of outcomes, we can, let's say, classify them into valid and invalid. So invalid outcomes we will not see in an architecture if it violates its memory model, but the valid outcomes we will see. So for each execution, as I said, we construct an execution witness, which is nothing but a graph. And if we can convert it to a sequential execution, well, it tells us something. We will see what. So let us now try to construct an execution witness for an execution that is showed over here. So here we have x equal to 1, we read the value of x. We set y equal to 1, we read the value of y. And the SC execution is like this. We set x equal to 1, we read the value of y into t1. This is read to be 0. Then we set y equal to 1, we read the value of x, and this is read to be 1. So what we can do is that we can convert this execution. So which is also, if you look at it, it's a parallel execution that we have converted to sequential, where the nodes are these instructions. Each one of these is a node. So this graph will have 4 nodes. We can then have edges between the instructions based on the orders that are guaranteed by the memory model. So I will discuss this part in somewhat more detail, but let's, for the time being, just go along with the flow. So what I'm trying to say over here is that different memory models impose different kinds of constraints on the execution witness. So we have different kinds of edges. So we can have two kinds of edges, global and local. So these are happens before edges, which means that let's say that if I write A happens before B, it means that event A happened first and then event B happened after that. So it does not matter when event B happened after event A. So as I said, we never look at exact time over here. So B could have happened immediately later or it could have happened after a very long time, right? So that doesn't matter, right? Whether it is just after A or after a very, very long time, this per se does not matter. The reason is that in all concurrent systems, we are only interested in the order, which means that it just happened after it or happened before it, right? And the timing doesn't matter, and mainly because we have so many non-deterministic events within the CPU that if we start putting constraints on the timing, these relationships will be very complex, and also we will not be able to guarantee all of those timings. So now let's come to global and local. So global happens before edge is added if, let's say, it is agreed to by all threads. In the sense, if all threads say that look, event A happened before event B, so let's call it GHB. So local happens before, we'll call it LHB. Local happens before, and global happens before, we'll call it GHB. So if we say that A happened before B, and this is globally agreed to, then all the observers, and in this case we have one observer on each thread, so all the threads will agree with this, otherwise they won't. All right. So there is a difference between global and local. So continuing to execution witnesses, there are different kinds of edges in the execution witness. So all of the edges, so we'll consider the program order edge first. So all of the edges are between memory operations issued by the same thread regardless of the address. So they can be same address, or it can also be different addresses, it doesn't matter. As long as these operations have been issued by the same thread, it is fine. So let us now look at the kind of program order edges that we add. So in general, the program order edge will be represented with PO in the execution witness, and we will add a program order edge between a read and a write, again issued by the same thread. We will call it PORW. Then we'll have PORR, which is read read, PO write read, PO write write, and from any instruction to a sync operation. So if synchronization operation, there is a global order. So I need to further talk about this part. So the program order edges, as we have been seeing, might be there or might not be there in a memory model. For example, the right to read program order edge is often violated. So this is clearly not global, and the execution witness will always contain global edges. So this needs to be kept in mind, that the execution witness will normally contain only global edges, and the right to read edge in most memory models is not global. But of course, in sequential consistency, all of these edges are global. Because we respect program order, all of these edges have to be global in SC. But in all other memory models, or let's say regardless of the memory model, the following edges are always global, which is from any instruction to a sync operation. So which means that the instruction fully completes, everybody gets to see the result of it, and then the synchronization operation executes. And similarly, POSI, which is again a synchronization operation to an instruction after it. So we have also seen other kinds of synchronization operations, which is not like a pure fence. In that case, these edges will of course change their character, but any edge from an instruction to a sync operation or vice versa, of course depending upon the type of the sync operation, is always global. Alright. So keeping these in mind, let us proceed. So what we need to broadly keep in mind is that we have some of these edges, which are these four, which are dependent on the memory model, right? So they are respected, they are said to be respected or global in SC, but the other two are global in all memory models. So let us consider an example. So nothing is clear without an example. So consider the following execution. So where we have a single thread. So we simply add edges, program order edges between the three different operations. If the memory model specifies that these edges are global. So we have WX1, WY1, so this is a write to write edge, and then we have a write and a read, so this is a write to read edge. So this execution witness will be valid if if the memory model is in SC, where we create a node for each memory operation and we add edges between them as per the memory model. So let us now look at another kind of edge called the read from edge, the RF edge. So the RF edge is a write to read edge for the same address, right? So program order edges were possibly for different addresses, but this is for the same address. But again, the program order edge was in the same thread, and this can also be across threads, right? So the RF edge, we can have two kinds, RFE and RFI. So in the RFE edge, we have read and write operations in different threads, right? So it is a write in one thread and a read from a different thread. And the RFI edge, we have the read and write operations in the same thread, right? So in the same thread, we have the write and then a later read. And needless to say, they are to the same address. So let's first look at a small example, and then I will explain more. So in this small example, we have a write and we have a read. and the final outcome is T1 is equal to 1. So in that case, what it means is that we are writing and we are reading, and that's the final, and the value of 1 is received by the other thread. So we can have a WX1, a RX1, and we can add an RFE edge. Alright. So an RFE edge can be added over here to signify the fact that we are writing and we are reading. So what we have also seen in the past is that if writes are atomic, the RFE edge is global. What this essentially means is that every write has one completion time associated with it. Then everybody will agree that look, the write happened and then the read happened after that. Right? So any read that is reading the value of the write, all of us will agree. But if this write is not atomic, then different threads will perceive this write to happen at different points in time. So the RFE edge will cease to be global, in the sense not everybody would agree that this write had fully completed. Fully completed means everybody had seen the value of the write before the other thread actually read. Right? So in this case, the RFE edge will not be global. So here, of course, an astute reader can ask that, look, if the write was not done, how did you read? Well, it was done with respect to this thread, but not with respect to other threads. Hence, this write was not global. So, if the RFE edge is global, if writes are atomic, if they are not atomic, the RFE edge is local. Similarly, RFI, so RFI is read from internally, so this is typically not global, okay. So even in order pipelines that have forwarding and so on of the kind that we have been seeing, so of course this is store to load forwarding, but nevertheless, load to, this is store to load forwarding. So in this case, if we have an LSQ, RFI will not be global, which means that internally we are forwarding the value of a write to a read within the pipeline. The rest of the world is seeing it much later, and this is, this is not a globally visible operation. So this means that a core can read its own value before other cores can, and whenever you read a value early, the corresponding edge does not remain global. In a sense, everybody does not agree that this is indeed a global edge, or let's say the write genuinely happened, genuinely completed before the read. Alright, let's look at a few more edges. So of course now our execution witnesses will become more and more expressive. So let us look at this particular execution. So thread 1 sets x to 1, thread 2 sets x to 2, and then we read the value of x, there is a fence, we read the value of x once again. So in this case, let's see what is the outcome. So the first outcome we read is 1, and then what we read is 2. So let us now create the execution witness for it. So we have the first write wx1, then we have the second write wx2. So since we read in this order 1 and then 2, we add a ws edge, which is a write serialization edge. So as we have seen in our discussion on PLSC, this edge is always global. Alright. So always this edge holds. So this edge is always global. And after that, the first write is seen by Rx1. So we add an RF edge going this way. The second write is seen by Rx2. So we add one more RF edge. And then we add a set of program order edges, because we have a read and then a fence. So there is a program order edge. And then we have a fence and then a read. So this is one more program order edge. So the WS edge is by definition always global, which is a direct consequence of PLSC and the requirements of coherence that ultimately came out of PLSC only. So what you further see is that this execution witness is acyclic. So what an acyclic execution witness basically means, that if we use the results of the topological sort algorithm, so the topological sort algorithm basically says that if we have a directed acyclic graph or a DAG, which is exactly the execution witness in this case, and if there are no cycles, it is possible for us to arrange all of these operations in a linear sequential order. So as you can see, this can be done. We can have Wx1, then we can have Rx1, then we can have Wx2, then we can have the fence, and then we can have Rx2. So it is possible to create a sequential order, which is sequential execution, which is equivalent to the parallel execution in this case. And as you can also see, this order is also legal, right? So we are respecting program order. In along with that, this is a legal sequential execution. So this execution is an SC. And furthermore, we saw how we can use three different types of edges, namely the WS edge, the RFE edge, and the program order edge, to create an execution witness. Now we will introduce the last kind of edge, which is a from read edge. So let us first take a look at the execution, and then we will see, we'll go further. So in this case, what we have is that we have two writes to the same location. We write 1 and then 2, and then we read the value of x. We read it to be 1. So what we can do in this case is that we have two write nodes, and then we have a write serialization edge between them. And the way we create an execution witness is that we add an RF edge. So this will be an RFE edge. It's external, right? Write to a read. And the interesting part is that given the fact that we read 1 and then to the same location we overwrite it with the value 2, we add the from read edge from Rx1 to Wx2. Alright. So as we have discussed in the past as well, in the execution witness, WS and FR edges will always be global regardless of the memory model. So let me write it. Regardless of the memory model, the FR and WS edges are global. Why is this the case? Well, this directly follows from the requirements of PLSC if you go back. And even so, it doesn't matter. We can have atomic writes, non-atomic writes, doesn't matter at all. From the requirements of PLSC, we brought in the requirements of coherence, that writes have one global order that is visible to all the threads, and all of them agree. So from that, it follows that both FR and WS, which is from read means from a read to a write, from a read to a write, and between writes to the same location, we observe a global order, right? So both FR and WS, they are accesses to the same location, and the execution witness, which anyway has only global edges, will always have WS and FR edges. Whether it has program order edges or RF edges, that is dependent on the memory model, right? And also, what kind of program order edges, we have tons of synchronization primitives, they have different behaviors, all of that is fine. But the key point is that the requirements of PLSC always hold. Why is it that the case? Because we want to maintain the abstraction that there is a single location for every variable. That might not be the case, in the sense we might have 20 physical locations for a single variable. But even if that is happening, an external observer should never get to know. From there, WS and FR come. Alright? Alright, so now we have looked at all the edges. So we would further like to introduce the synchronization edge, which is important. So we will see it is extremely important to tie all of these things together. And the synchronization edge can be mentioned very easily over here with this example. Let's say we set x as 1 and y as 1, and let's assume that program order holds between the right to x and right to y. So let us assume now that y is a synchronization variable. So we will specialize this in the later lectures on how do we say that one is a synchronization variable, but let's assume for the time being that y is a synchronization variable. So what we will do is that we will introduce a version of a write, a version of a store, which can be thought of as a synchronization store, in the sense that any store, of course, with additional directives. So x86, for example, allows you to specify the lock prefix. If that is uh, if that is mentioned before a load or a store, then the address automatically becomes a synchronization variable. So let's assume that that is specified. So this is a synchronizing variable. So then we read the value of x and we read it to be 1. So what we do is we add a program order edge between the wx1 and wy1. So recall that we will not have a ws edge because these are different addresses. Then we have an RF edge, which is also a synchronizing edge, right? The latter being more important. So an edge can also be of multiple types. So an edge need not have a single type, it can have many types. So it's a synchronizing edge. And again, between reads, let's assume that program order holds. So in this case, this execution witness will be valid, because if we add the final edge, which is an RF edge, an RFE edge to be more precise, between the write and the read, we will not have a cycle. So this basically means that all of these operations can be arranged in a linear order, and you will furthermore find that it will be legal as well, and it will follow program order as well. So here, what is the assumption? That y is a synchronization variable. How did we specify that? Well, let's be slightly vague about it right now. All that I would like to mention is that we will use special synchronizing loads and stores in the place of normal loads and stores. So x86 has a lock prefix. The lock prefix allows us to convert a regular load store to a synchronizing load store. All updates to such sync variables are globally ordered. So let us assume. So furthermore, many memory models assume that all synchronizing accesses or updates to sync variables are in SC. So we will make a similar assumption here in our discussion as well. So just to summarize, what are all the edges that we have introduced? So we have introduced 5 kind of edges primarily. So we have introduced a program order edge, which is between instructions of the same thread, right? So that's important. Same thread. Doesn't matter. It can be same addresses, same set of addresses, different addresses. Doesn't matter. But same thread. Right to read. Well, it's a right to read dependence. It can be, all of these can be across threads. These 4 across threads. So the write to read operation, there is a dependent same address across threads, write to write, read to write. All right. So across threads, we don't have a read to read order because it doesn't matter in which order you actually read. So that's not important. So what we do over here is that these are to the same address, and also a synchronization edge between sync operations. It should be the same. The synchronization variable should have the same address, so that would make it a sync operation. All right. So to summarize, we will create an execution witness, which is a graph, and each operation, memory operation, is a node. We'll have these 5 kinds of edges, and then we'll analyze the entire graph. Most importantly, we will search for cycles, and we will use the results from topological sorting, which say that if a graph does not have cycles, it is possible to arrange all the operators in a linear order, such that if there is a path from operation A to operation B in the graph, then operation A appears first and operation B appears later, right? So we would keep on discussing this several times, but the idea of topological sorting should be clear. All right, an even bigger, grander summary. So the WS, FR and SO edges are always global. WS, FR follow from PLSC and SO follows from the way that our hardware implements synchronization operations. So they are always global. Some subset of program order edges are global. So let us call that subset PPO. And some subset of the RF edges are also global. Let's call them GRF. For SC, GRF is equal to RF in the sense that both RF external and RF internal are global. And PPO is equal to PO in the sense all program order edges are global. So finally, our global happens before relationship, which is exactly what the execution witness will capture, will comprise all the program order edges which are global, all the RF edges, also called the data flow edges that are global, data flow between a write and a read, and the WS and FR edges which have to be global because of coherence and PLS. Alright. So this is our global happens before order. So what we do is we take an execution, a parallel execution of course, we create an execution witness, we add all the edges as per these relationships. PPO and GRF are prescribed by the memory model. So we add those edges and then we search for cycles, right? So this is where we are right now. So let us further elaborate on the fact that let's say after creating the execution witness, why are cycles all that important? So here we'll use the classic computer science result of topological sorting, which says the following. So note that all of these graphs are directed graphs, they are not undirected graphs. So if a graph does not have a cycle, we can arrange all the nodes in a linear sequence such that if there is a path from operation A to B in the graph, then A appears before B in the linear sequence. So what does it mean that there is a path from A to B in the graph? It means that there is a sequence of happens before edges, global happens before edges between A and B, and it means A happened first and then B happened later. So if I can arrange them in a linear sequence of operations so that A appears first and B appears later, and the same holds for all pairs, then we can say that this is a possible order of completion times of these operations. In a certain sense, what we can say is that this is most likely it's a feasible execution in the sense if let's say these operations were to complete like this, then no happens before relationship would be violated. So this is a sequential execution, no doubt. Okay. And the way that we convert a graph into a sequence is using the topological sort algorithm, which maintains the same happens before orders. So what we have here is we have an acyclic execution witness, and that leads that essentially leads to a sequence of operations. All right. So let us now look at the implications of mapping a parallel execution to a sequential execution. So what we did is that we extended the discussion of the previous section and we took a parallel execution, created an execution witness out of it. So in the execution witness, the edges were added as per the constraints imposed by the memory model. And then from this, we first checked for cycles. So we said that look, if there are cycles, we can never have a cycle of happens before relationships. That's not possible. Otherwise, it will be a given operation happened before the same operation itself. So cycle happens before relationships would look something like this, right? So regardless of the other operations, finally it will come back to it. So it will basically mean that a given event A happened before the same event, which of course is not possible. So we cannot have a cycle of happens before relationships. Because of that, if the execution witness does not have a cycle, then we are saying that the execution is feasible. Well, why? Because we can do the topological sort on the graph and arrange the operations in such a way that if there is a path from operation A to B in the execution witness, A appears before B, and this holds for all pairs. So this is a possible order in which the instructions complete, but this is not, unfortunately, a legal sequence all the time. It will be legal, of course, if the writes are atomic, but if the writes are not atomic, which means that if a write appears to complete at different times to different threads, this will not be a legal sequence, so legality will be violated. So this is a problem. But the key important theoretical point over here is that we establish an equivalence between a parallel execution and a sequential execution, not necessarily legal, and the execution is feasible according to the memory model. So this still, our original aim of finding the set of valid outcomes is still satisfied. The reason is that, look, what we do is that we look at all possible ways that a given piece of code can execute. We create the execution witnesses. All of this can be done automatically using a software tool. And then for each one of them, we can check for cycles. So there is no reason to sequentially enumerate those operations. We can if we like. And furthermore, if the writes are atomic and the execution is legal, even though the program order doesn't hold, that is still fine. If that gives us more tools and more theoretical insights, we can do that. But even at the level of the execution witness itself, if it does not have cycles, it means that the execution in terms of the outcomes is valid. So this does give us a very strong and powerful tool to find out when a given execution is valid for a particular memory model. All right. So this is where we would like to end this part with regards to the validity of executions with respect to certain memory models. And then there are also other aspects of an execution that we shall look at next. But at least from the point of view of memory models, we established an equivalence. And then as long as the execution witness does not have cycles, which means that there is no cycle of global happens before edges, we are fine. This essentially indicates to us that a given execution is per se valid, right? The outcomes are valid, they are allowed, which is the key thing that we wanted to theoretically investigate in this part of the lecture. So let's keep going and look at a few more criteria for validity. This was one, but there are a few more as well. So next we will look at accesses to a single location, and we'll also look at data and control dependencies. So let us create a new tool called an access graph, which in principle is similar to an execution witness, but it is different. So it contains all accesses to the same location. All accesses are to the same location. We can have multiple threads. So I have shown a diagram for a single thread, but we can have multiple threads as well, no issues. So consider all the operations issued by a single thread. So we'll consider all the accesses initially for address X. So clearly this will not be there. So I'll have WX1 and WX2. So we will introduce a new kind of edge. So instead of program order edges, we will have UP edges called uniprocessor edges. I'll discuss in a second why. So it is edge between accesses to the same location in the same thread. So mind you, this is accesses. So this can be read, write, write, read, read, anything. It's two accesses to the same location within the same thread. So we'll create a new kind of edge and we will call it the UP edge, which of course does capture program order, but it is again accesses to the same location within the same thread. So what we see over here is that we write 1 first, then 2, we add a UPH, and then so I'm treating this simplistically as several instructions, but simplistically as one instruction in the access graph where we just read the latest value of x, which is 2. So we add one more UPH, and finally we write 4. So as you can see, I have extracted 4 instructions. I have added uniprocessor edges, and let's take it slightly further. So here is what I claim, which is a simple generalization of the discussion that we had in the previous section on SC. So pretty much in SC we had program order. So we are now looking at PLSC, which is all the accesses for a single location. See, here also WS and FR are global, and program order in this case is UP, and in SC, since all of RF is global, so we have program order here as well. All right. So what is it that we are trying to do? What we are trying to do is that we are trying to look at all the accesses to the same location. Doesn't matter, it can be one thread or it can be several threads, that doesn't matter. So similar to SC, we can define PLSC over here. Of course, PLSC will be confined to everything for the same location. So instead of PO, we will use UP. And since all RF relations are global in SC, they will be global in PLSC also, at least in the definition. So this is global. And finally, we will add make FR and WS global. So this for us is PLSC. So what we have seen before this discussion is that PLSC is always respected regardless of the memory model, right? So regardless of the memory model, we always respect PLSC, that is point 1. And because of that, when we create an access graph, which will only have accesses to, let's say, a single location, doesn't matter, many threads, we will have a very similar graph as the execution witness, right? So like the access graph is pretty much an execution witness confined to a single location, right? And so in that case, we'll add our FRWS edges, of course, RF edges, of course, they will be global, and our PO edges, and we expect, so there is no memory model with respect to accesses to a single location because PLSC needs to hold. So we expect that the access graph will not have any cycles. Why? Because if it has cycles, PLSC doesn't hold. Right? Recall our discussion in slide number 74. So here the access graph for PLSC to hold, it implies that there are no cycles. So let us now look at data and control dependencies as well, and then try to create a different kind of graph. Alright, so we have looked at the access graph in the previous slide, and the access graph was same as an execution witness, right? So it's an execution witness for a single variable. So in this case, of course, PLSC has to hold, which is essentially sequential consistency for a single location. And this part should be self-explanatory by now. So let us now consider one more example. So in this example, we'll have UP edges, uniprocessor edges, and we will have multiple threads, the threads T1, T2 and T3. So in thread T1, we write to X and then read, T2 we just write, and T3 we read twice. So is this outcome allowed? Let's see. So T1, T2, T3. So T1 is equal to 2. Here we read 1 first and then we read 0. Is it allowed? Well, so note the UP edges. So note the UP edge from WX1 to Rx2. So they are a part of the same thread. So given the fact that they are a part of the same thread, we see this uniprocessor edge to enforce the dependency. And then we have WX2, a write serialization edge over here, and then write to read edge, because instruction B reads the value produced by instruction C. So there is no cycle over here, but we will see a cycle when we consider thread T3. So thread T3 reads 1 first, so we see an RF edge and an FR edge. Right, so why an RF edge? Because there is a write to read dependence over here, and an FR edge because there is a read to write. Right, so we read an older value and then WX2 is a later value, and then a UP edge to the subsequent read where we read as 0. So this is where the fun is. So because we read as 0, there will be an FR edge from this access to WX1, because we read 0 first and then 1 is written to the location. So we do see a cycle, and the cycle goes all the way up like this way, and this way. So given the fact that we have a cycle in the access graph, PLSC is violated, and consequently this execution is not allowed. All right. So now we have seen PLSC, which is very important if we consider accesses to a single location. So we are not done yet. There is something called a thin air read, which we shall see next. So let us now also consider data and control dependencies. So while considering data and control dependencies, what we see is that so we are looking at a program with 2 threads. So here we read X first. So let us assume that this read, so this read will be affected by a load operation. So let us assume that we also have value prediction over here. So if you have value prediction, so what happens in value prediction? Well, in value prediction, we predict the value early, and later we read the value from the memory system and we verify. So in this case, we read the value, but that might take time. So in the time being, we predict and we verify later. So for uniprocessor executions, we have been claiming that value prediction is absolutely correct. Just the paradigm itself. The reason is that we will never read a wrong value, because we are always verifying a value before committing. Is that the case for multiprocessor executions? Let's see. So let's assume that the value is stored in the register T1, and if T1 is equal to 1, which is the if statement. So in this case, what we do is we set Y to 2. So let's assume we find it to be 1 in this execution, right? And then once we set Y to 2, let's assume we have atomic writes. So in this case, we will have an RFE edge from WY2 to RY2. So let us further assume that our memory model is such that we do not have a read to write ordering between accesses to different addresses in the same thread. And a lot of memory models, which are called weak memory models, as we shall see, they will not have this ordering. So we have not added any edges in T1, right? So in T1, no edge per se has been added. Now let us look at thread T2. So in this case, we have a fence, program order edge, 2 of them are required. So in this case, what we do is we read the value to be 2. So that justifies the RFE edge. And then we have 2 program order edges. And then we write 1, WX1. And then what we actually get to see over here is that WX1 supplies the value to RX1 via an RFE edge. So first, let's look at the outcome. So the outcome, of course, is that T1 is equal to 1, as you can see, and the outcome is T2 is equal to 2 because of the RFE edge. So this execution witness over here does not have a cycle. So we might be tempted to say that this is a legal and feasible execution, but the answer is that it is not. Why is that the case? The reason that that is the case is that there is a clear break in what is called causality. A causality is essentially a cause-effect relationship, right? So anytime there is a cause and effect relationship, we call it causality. And there is a clear break. Let me explain why. So the reason is that we read the value of x into t1. So we assume that at this point x is already equal to 1. After that, since x is equal to 1, we set y to 2, and then we read y to be 2. Then of course we have a fence, so we have a strict program ordering, and then we set x to be 1. So there is a, as you can see, there is a causal link which goes like this. So one event after the, so this first this event, then this, then this, then this, then this, then this. But the point is, at this point, x is actually not equal to 1 if you think about it. The reason is that we set x to be 1 at the end of the chain of this causality, at the end of the causality chain, right? In the sense, first something happens, then something, and then at the end, we set x to be 1, but x was not 1 at the beginning. But how can this execution happen? Well, the way that this execution can happen is as follows. We predict the value of x, so we predict it to be 1, then we keep executing. After predicting it to be 1, what we do, so what we do is that we go and speculatively perform the write. So in this case, we perform the write early, and we do not wait for the instructions prior to the write get committed. So this does happen in extremely high performance processors, where this read to write order is violated, and they do perform early writes. And after that, what we see on the side of T2 is that in T2 we perform the load and then the fence, and then we write 1 to x. And so at the time of verification of this instruction, we will always read x to be 1, and this instruction would deem to have been verified, but that will actually not be the case. The reason that will not be the case is basically because when we originally read x, it was actually 0, and then this is kind of a spurious value, right? So x equal to 1, or rather t1 equal to 1, appears to have been read from nowhere, and so that's the reason it's called a thin air read. Because if you think about it, t1 should have been read equal to 0, because x became 1 just because we assumed that x is 1 over here, but that was a wrong assumption, because at this point x was actually equal to 0. So this value kind of has been picked out of thin air. So that's the reason it's called a thin air read. And such kind of an execution would be valid as per our execution witness logic, right? That this execution witness is acyclic. But we would still like to prevent such kind of thin air reads. So I would further like to say that the problem of having thin air reads also does arise when, for example, we are implementing a virtual machine like the Java virtual machine and so on. So that is why this is a general theoretical concept where essentially there is a break in causality, and the reason being that we assume a variable to have a certain value, and later on the assumption is proved to be correct just because we assumed, right? So this is of course not the right way. It's kind of a circular logic which is incorrect, and that's why such thin air reads have to be prohibited. So what I would request all the listeners of this video to do is to take a look at this example, convince themselves that this example is actually not correct, but our execution witness method says that it is correct. So we have to do something in addition to this to stop this from happening. Let us now create a causal graph, where in the causal graph we'll have three kinds of edges. So we love creating graphs, so we keep creating graphs of different kinds. So let us compare a causal graph with the previous figure. This is the execution witness, this is fine. But we take the execution witness, we add three kinds of edges. So we keep the RF edges because they determine data communication, right? So they determine causality in the sense I write and then I read, all right? So this causality is maintained. Then we add all the global program order edges, so called GPO. So I've also referred to this as PPO previously in the slides. So PPO is called preserved program order, which for that particular setting was correct. But what should have probably been used and which was more relevant was GPO, all global program order edges. Even the PPO was not wrong. But we will prefer the term GPO, and in the book also I've used GPO. So what are the edges we add again? We add RF because so what is the point of view, right? It's important to define the observer here and the point of view. So the observer is basically uh, an observer on all the threads is only looking at the communication of data in the sense that I read something and then what are all the operations that are dependent on the read. So one is that I might be communicating some data the way that I'm doing from WI2 to RY2. So then after that, so the observer will basically change the point of observation from WY2 to RY2. All the global program order edges in the sense that RY2 needs to complete, then the fence, then WX1. And also a set of dependencies, which means one instruction needs to complete, then the dependent instruction, in this case the if statement, and then the instruction in the body of the if statement. All right. So this is a different kind of graph. We have not really seen this kind of a graph before. So this is called a causal graph. So here we have RF edges, which in this case are global. The reason is that the observer is not really looking at other threads about what they think about a write. It is only looking at the flow of data, right? So think of the observer pretty much as sitting on the forward slice of the read, right? So basically, wherever whoever is affected by the read, data or control, the observer is sitting on the forward slice and tracking it. So pretty much what a thin air read basically means is that a read is a part of its own forward slice, right? Which is never the case, which will never happen. That no instruction will kind of be a part of its own forward slice via a path like this. So that is exactly what we are seeing. That from the read, there is a path from the read to the read. So read is a part of its own forward slice, and there is a path from the read to a read that passes through other nodes. So what the observer would do in this case is sit on the read and simply start observing all the instructions that are dependent on the outcome of the read. That would include data and control dependencies, communication behavior, write to read, as well as global program order edges. So we'll create a causal graph out of these three kinds of edges. And this, needless to say, needs to be acyclic, because if it is cyclic, it means that there is a break in causality. So there is a thin air read basically. So now the time has come to put all of it together. All right. So to put all of it together, so we are looking at the validity of an execution. So we look at the validity of an execution from several points of view. In the sense, we define different kinds of observers with different points of view and different capabilities. So first we check if it satisfies the memory model. Right? So different architectures have different memory models. In this case, the execution witness needs to be acyclic. We have seen that. Then does PLSC hold for all memory locations? Yes, it has to. Otherwise, the notion of a single shared memory will stop to hold. So in this case, all access graphs are acyclic. Then again, we don't want thin air reads. So in this case, the causal graph will be acyclic. All right. So we have to ensure that for every execution, these three hold. Alright. So in a certain sense, these three conditions hold, that we are satisfying the memory model, we are satisfying PLSC, and furthermore, we do not have any thin air read. So there is no break in causality. So these are pretty much the three most important conditions of any execution being correct on a multiprocessor system. And we also think about it, for a uniprocessor system, all that we need is PLSC, because for every read we just need the latest write, or if there is a single thread running on a multiprocessor system, we also need PLSC, not the others. So they are not really relevant in this case. So in this case, uh, all single threaded programs will work correctly on a multiprocessor system. That is something that is given if PLSC holds. But in addition, if you have multiple threads and multiple cores, we have to satisfy the memory model and avoid thin air reads. All right. So in the next lecture, we will move on to cache coherence. So we have finished the first two parts of this chapter.